Hey guys, I welcome you to my YouTube channel, Learn Physics with IBM. And today I gathered the courage to solve past papers. I'm solving May-June 2023. And today I'm starting with paper 2-1. I'll solve all the three on the same day, so there's no problem with that. So without wasting time, I would like to take you to the question paper. So this is the question paper, and this is May-June 2023 and it is component 21. This paper was very easy that one of my students scored 60 out of 60 and many of them got above 55 because they practiced the solved past paper questions that I had recorded per topic. So if you're a teacher, you can encourage your students to practice the solved past paper questions, especially those who have a lot of time. Those who are sitting in May-June next year, they can still make it if they practice the topical past paper questions. So this is what my students did in May-June series, and they were able to excel in this exam. So without wasting time, let's get started. It's a paper which is out of 60. I will not go through the data which you always used to. You can check in the question paper for the data. Or before, my name is IBM. I'm the one solving this paper. This is IBM. I'm based in BSU, as my current school is called BSU. You can find out what BSU stands for. So this is the data. I'll not go through the data given. So number one, define power. So we know that power is the work done per unit time. So this is simply work done per unit time. Or you can simply say power is the rate of doing work. Power is the rate at which energy is transferred, because work done is energy in motion. So rate of doing work, rate at which energy is transferred, that is still power. Use the definition of power to show that the SI base units of power are kilogram meters squared per second cubed. So we have already seen that power is the rate at which work is done. So, and of course we know that work done is force times distance in the direction of the force, then divided by time. So it means, and we know that force is mass times acceleration. So we know the base units of force. The base units of force will be the base units of mass, which is kilogram, times the base units of acceleration, which is meters per second power minus 2. And we know the base units of distance, which is the meters, and the base units of time, which is the second. So we just combine. So it means the base units of power would be kilogram meters per second squared times meters divided by seconds. So when you simplify this, it simplifies to kilogram meters squared s minus 2 divided by s, that is s power minus 3. So that is what we obtain here. So the answer is correct. The intensity of a sound wave moving through a gas is given by this equation. We have seen this equation in the past paper questions that I've solved, especially in physical quantities and units, where f is the frequency, a is the amplitude, v is the speed of the wave, and k is a constant that depends on the gas. Determine the SI base units of k. So I'll begin by making k the subject. So k is going to be intensity divided by f squared, a squared, and v. So I'll list the base units of those quantities. F is a frequency. The base units of f is seconds power minus 1 per second. That is the base units of frequency. Somebody will write hertz, but it's per second. Then amplitude is a distance, so it is in meters. Then v is speed, which is meters per second. Then we have intensity. We know that intensity is equal to power per unit area. The power of a wave per unit area, that is intensity. Now we know the units of intensity. So it means, we know the units of power. We know area is meters squared. So the units of intensity are going to be power, which we obtained above. That is kilogram meters squared per second cubed divided by the area, which area is meters squared. So when we simplify, it means the units of intensity, meters squared has cancelled out. So the units of intensity are going to be kilograms per second cubed. It's kilogram per second cubed. So that is the intensity. So we can now substitute to find the units for K. So the base units for K will be for intensity, which is kilogram per second cubed divided by F, which is S. So because it's F squared, we shall square S power minus 1, so it will be S power minus 2. Then amplitude is meters, but it is squared, so it is M squared. Then times V, which is M S power minus 1. So we just try to simplify the numerator, the denominator. So it is kilogram S minus 3 divided by M squared times M, that is M power 3 times S minus 2 times S minus 1, it becomes S minus 3. So you will notice that S minus 3 cancels out. So this simplifies to kilogram. Because it is kilogram divided by M power 3, it becomes M power minus 3. So the answer here is going to be kilogram M minus 3. So that those will be the base units of SI base units of K. A rigid uniform beam of weight W is connected to a fixed support by a hinge as shown in the figure. So we can see the diagram. Before we read even the questions, we can see which ones are causing clockwise moments. A compressed spring exerts a total force of 8.2 newtons vertically upward. So there's a force here from the spring which is going to be 8.2 newtons. A block of weight 0.3 rests on the beam. The right hand end of the beam is connected to the ground by a spring at an angle of 30 degrees to the horizontal. The tension in the string is 4.8 newtons. The distances along the beam are shown in the figure. The beam is in equilibrium. That means the resultant force is 0. The resultant moment should also be 0. Assume that the hinge is frictionless. Show that the vertical component of the tension in the string is 2.4. So this is the string. We have to find the vertical component. In other words, we resolve the vertical the tension here in the vertical. It will even point downwards. So using the angle of 30 degrees, resolving to the horizontal, it will be cos. To the vertical, it will be sine. So to the horizontal, it will be 4.8 cos of 30. To the vertical, it is going to be 4.8 sine of 30. We are interested in the one which is in the vertical. So I'll simply say the component is going to be equal to 4.8 sine of 30, which I'm very sure sine of 30 is a half. So when I press my calculator, I get 2.4 newtons. By taking moments about the hinge, determine the weight W. So let's go and take moments about the hinge. So we are taking moments about this fixed point here. So the tension from the spring, the force from the spring will exert a moment in this direction because it is pushing the beam upward. So it will cause an anti-clockwise moment. The weight is pulling the beam downward, so it is causing a clockwise moment. The 0.3 Newton is also pulling it downwards. It is causing a clockwise moment. The force sine 30 is pulling the beam downwards. It is causing a clockwise moment. The 4.8 cos 30 has no moment because its line of action it is in the horizontal, which goes through the beam. So we have 1, 2, 3 clockwise moments and 1 anti-clockwise moments. For equilibrium, according to the principle of moments, the sum of clockwise moments should be equal to the sum of anti-clockwise moments if the body is in equilibrium. So I have the weight W, its perpendicular distance is 0.1 plus 0.5 from the fixed point. I have 0.3, its perpendicular distance is 0.2 plus 0.1 plus 0.5 from the fixed point. I have 4.8 sine 30, its perpendicular distance is 0.4 plus 0.2 plus 0.1 plus 0.5 from the fixed point. I have the one which is causing anticlockwise moment, which is 8.2 newtons. Its perpendicular distance is 0.5. So these should be equal. So taking moments above the fixed point, I have the weight. Its perpendicular distance is 0.5 plus 0.10 or 0.50 plus 0.10. Then I also had a 0.3. Its perpendicular distance is 0.20 plus 0.10 plus 0.50. I also had 4.8 sine 30, which is the same as 2.4. So 2.4 times its perpendicular distance, which is, I will just add it from here, 0.4 plus 0.2 plus 0.1 plus 0.5, that is 1.2. So I'll just say times 1.2 perpendicular distance. So this should equal to the anticlockwise moment, which is 8.2, and its perpendicular distance is 0.50. So we can simplify this. So this is W times 0.6 plus 0.3, 0.8, 0.3 times 0.8, then plus 2.4 times 1.2 should be equal to, I think 8.2 times 0.5 is the same as 4.1, it is a half. So I'll just simplify to find W. I will say 4.1 minus, I'll subtract everything I expect, 2.4 times 1.2 minus again 0.3 times 0.8, then I divide by 0.6. So I am getting 1.63 recurring. So W is 1.63 recurring, which is just approximately 1.6 newtons to two significant figures. So I'll just write here 1.6. Calculate the horizontal component of the force exerted on the beam by the hinge. I've already showed you the horizontal component. So the component here is 4.8 cos of 30. So 4.8 cos of 30 is simply 4.2. So I'll just write here 4.2. The spring obeys Hooke's law and has an elastic potential energy of 0.32 joules. Actually, the tension, the compression of the spring. So we know that the spring has elastic potential energy, and elastic potential energy is equal to a half kx squared, or it is going to be a half times fx, depending on what is given. Since I have the forces, I don't have the constant, I'll ignore the constant. So I'll just say the elastic potential energy, which is given as 0.32, should be equal to a half times the force in the spring, which was given as 8. The force in the spring was given as 8.2 newtons in the previous part. So this is times 8.2 newtons times x. So I want to find x. X will be 2 times 0.32 divided by 8.2. So 2 times 0.32 divided by 8.2. So this is 0.078. 0.078. So that will be the compression. The string is cut so that the spring extends upwards. This causes the beam to rotate and launch the block into the air. The block reaches its maximum height and then falls back to the ground. The figure shows part of the motion of the block in the air shortly before it hits the horizontal ground. The block is at a height of 0.09 meters above the ground when it passes through point A. The block has kinetic energy 0.044 joules when it hits the ground. Air resistance is negligible, that means acceleration is going to be constant and it will be g. Calculate the decrease in gravitational potential energy. So we know that the decrease in gravitational potential energy is given by mg times the decrease in the height h. Of course, mg is the weight. If we have been given the weight, it would be fine, but I think we have the mass. We have the weight of the block, which is 0.3, so I will not even waste time. So, and mg is the weight of the block, which was given as 0.30 newtons. So I'll just substitute mg 0.3. So this is going to be 0.30 times the decrease in the gravitational, in the height, which is 0.09. So I'll just press my calculator. 0.3 times 0.09. So this is giving me 0.027, 0.027, 0.027 joules. Use your answer in C-Roman 1 and conservation of energy to determine the speed of the block at point A. So at point A, it was already moving, so it means it had kinetic energy. Then at point B, it is gaining kinetic energy as it loses its gravitational potential energy. So I know that kinetic energy, Ek, is equal to a half mv squared. So the potential energy it has lost from B to A must also have been converted into kinetic energy. But the kinetic energy it has at B is 0.044 joules. That means what has been lost as gravitational potential energy must have been the kinetic energy at point A. So the difference between those two must be equal to the energy must be equal to the loss in energy. So we are going to have that the energy is simply going to be 0.044, or the change in kinetic energy is 0.044 minus 0.027, and I think this is 0.044 minus 0.027. This is going to be 0.017 joules. So using the expression there, I'll have that V is going to be twice K, twice 2 times the energy, which is 0.017, divided by the mass, which mass is, you know that the mass is the weight, divided by G. The mass of the weight of the block is 0.3 divided by G, which is 9.81. So I'll say 0.3 divided by 9.81. So I'll check my calculator. 2 times 0.017 divided by 0.3 divided by 9.81. Then square root of the answer. So I'm getting 1.054. So speed here is 1.054, or we can write 1.1. the answer is most likely 1.1 meters per second. Alternatively, I could use another alternative method. Let me change the color for the other method. So first of all, I will find the speed with which it reaches point B. Or sorry, I will use the equations of motion. Since the acceleration is constant, I will use v squared equals to u squared plus 2as. Velocity at B is the speed at B. I'll first get the speed at B from kinetic energy is equal to a half mv squared. I'm getting the speed at B. I know the kinetic energy at B. I'm trying to find the speed at B. So the speed at B is going to be the square root of, it is going to be the square root of, because the kinetic energy is 0, so it will be 2 times 0.044, that is the kinetic energy at B, divided by the mass which is still 0.3 over 9.81. So I'll just press my calculator. 2 times 0.044 divided by 0.3 divided by 9.81. So the speed, okay, I will not find the square root. Let me just find v squared, because I know I need v squared in the equation in that equation of motion. So I'll just maintain v squared. I will remove the square root. So this is v squared is 2.88 meters per second. 2.88 meters per second. My writing bad. 2.8. Sorry about this. My machine is now finding issues. So it is 2.88. So that is v squared. So I'm now going to substitute in this equation here. I now know the velocity at B, which is final velocity. So I will say 2.88, which is v squared, is equal to u squared, which I want to find. Because it was falling, the acceleration is positive. So I will say plus 2 times acceleration, which is 9.81, times s. Of course, it has fallen through a vertical distance. I'm considering vertical motion. It has fallen through a vertical distance of 0.090 from the diagram. So I'm just going to press my calculator to find u squared. So I have 2.88 minus, open brackets, 2 times 9.81 times 0.09. Then I find the square root because I want u. So still I'm finding u as 1.05 or 1.1. So you could first use the kinetic energy at B to find the speed at B. Then since the acceleration is constant, use the equation of motion to find the speed at, or the initial speed at A. As simple as that. By reference to the force on the block, explain why the horizontal component of the velocity of the block remains constant as it moves from A to B. By reference to the force on the block, of course, if air resistance is negligible, the only force acting on the block is the force due to gravity. And you and me, and we know that the force due to gravity acts in the vertical, so we shall simply say the only force acting is gravitational force. The gravitational force or the weight. which only acts in the vertical. So the only force acting is the gravitational force, which only acts in the vertical. What does this mean? No acceleration in the horizontal. And if there's no acceleration in the horizontal, it means the velocity component remains constant. The block passes through point A at TA. So remember at A it had a speed of 1.1, which we have seen, and at B we have seen that B it has a speed of 2.88. On the figure, sketch a graph to show the variation of the magnitude of the vertical component. This was of course in the vertical. In the horizontal, it remained constant. Of the block with time t equals to Ta and to t equals tb. Numerical values are not required. So at Ta the speed is going to be lower. At tb the speed is going to be higher. Since acceleration is constant, because acceleration is equal to g, which is constant since there is no air resistance, so it means the gradient of this is going to be constant. And how do we show constant gradient? By drawing a straight line. So since the acceleration is constant, it means the gradient of the velocity time graph should be constant. Therefore, this should be a straight line. So I'll just draw a straight line. So the answer is going to be a straight line. A block is pulled in a straight line along a rough horizontal surface by applying a force X. So we can see the figure. Air resistance is negligible. Assume that frictional force exerted on the block by the surface is constant and has magnitude 2 newtons. So the friction has magnitude 2 newtons. Of course, we know that the friction, if force X is acting forward, then the friction is going to act in the opposite direction. So this is going to be 2.0 newtons, not 20, 2.0 newtons. Okay. The variation with the time t of the momentum p of the block is shown. So this is momentum against time. State Newton's second law of motion. Of course, remember Newton's second law is force is equal to ma. So that is the rate of change of momentum. For the resultant force is directly proportional to the rate of change of momentum. So I'll simply say resultant force on an object is directly proportional to the rate of change of momentum. The resultant force, it must be resultant, or the net force on an object is directly proportional to the rate of change of momentum. In other words, force is directly proportional to the change in momentum over time, but this force must be the resultant force. Use the figure to determine for the block at time t equals to 2 seconds, the magnitude of the force. Remember, the force is the rate of change in momentum. We see that at 2 seconds, it is a straight line passing through. So I just find, it means the rate of change is constant because it's a straight line, the gradient is constant. And the gradient is going to be the force. So I just find the gradient. I can use any pair of values. So the force can be 6 minus 0 over 4 minus 0. Or the force will be, somebody may want to use 2. It can be 3 minus 0 over 2 minus 0. It gives you the same thing. Somebody will also choose to use another pair of points, say 6 and 3. So the force can be 6 minus 3 divided by time is 4 minus 2. you get the same thing. So I'll simply say the force is equal to the rate of change of momentum. So force equals to the rate of change of momentum. So I'll just take a simple value. So I'll take 6 minus 0 over 4 minus 0. I said you can choose any other pair of values, or you could take 3 minus 0 over 2 minus 0, or any other. Because it is a straight line, the gradient is constant. So I think this is going to be 3 over 2, which is 1.5. So the resultant force is going to be 1.5 newtons. Then the force X. So remember, we know that resultant force, the resultant force is going to be equal to the forward force, which is force X, minus the frictional force or the resistive force. So it is going to be force X minus the friction force. So the resultant force is 1.5, is equal to force X minus the frictional force, which was given as 2.0. So it means force X is going to be 1.5 plus 2.0, which is going to be 3.5. So force X is going to be 3.5 newtons. On the figure, sketch a graph to show the variation of force X with time t, with time t from t equals to 0 to t equals to 6. Okay, so let's first go back here. So we know that we have already seen that between t equals to 0 to t equals to 4, the force X is t equals to 0 to t equals to 4, force X is equal to 3.5 newtons, because the resultant force is constant, so the force X is going to remain constant at 3.5 newtons. Then from t equals to 4 to t equals to 6, we see that the resultant force is 0 because it is a horizontal line. The resultant force is 0 because it's a horizontal line. It means the rate of change in momentum is constant. Is 0. So for a horizontal line here, it means force is going to be 0 because force is equal to change in momentum over time. And since the change in momentum is equal to 0, so the force is going to be 0 here, the resultant force. So it means force X, remember force X is equal to the resultant force plus the friction. So it means force X, since the resultant is 0, it means force X is going to just be equal to the friction. And in this case, the friction was 2. In this case, the friction was 2. So force X is going to be 2 newtons for this part here. For this part here, we have already seen the resultant force is constant, and it was 3.5. The resultant force was constant, so force X was 3.5 newtons. So let's just go back here and sketch. Let's say that between t equals to 0 to t equals to 4, the force X, remember force X from just the previous part above us, force X is equal to the resultant force, F resultant plus friction, F friction. So because the resultant force is constant and it was 1.5, and the frictional force is constant was 2.5, between t equals to 0 to t equals to 4, Fx is going to be 3.5. So, and it is constant. So this is going to be 3.5 and it is constant, so that will be a horizontal line. Okay. Then we have said between t equals to 4 to t equals to 6, we saw from the previous graph it was a horizontal line. A horizontal line means F resultant, which is change in momentum with time, is equal to 0 because the momentum is not changing. So the resultant force is 0. So it means Fx, which is equal to the resultant force plus the frictional force, which was not changing, it was 2.0. F in the x will be 2.0 and it will be constant because the friction does not change. So at t equals to 4, the F is 2.0 and remains constant because the friction is not changing. So this is going to be another horizontal line. So just have a step. Just have a step like that. So that is going to be the graph. A beaker in air contains a liquid. The base of the beaker is in contact with the liquid and has area A as shown in the figure. The liquid has density ρ and fills the beaker at a depth h. By using the definitions of pressure and density, show that pressure is equal to that. First of all, from definition of pressure, pressure is equal to force over area, the force acting normally per unit area. This force is going to be simply the weight of the liquid and the container over the area, and we know that of course the weight is going to be m times g. But we also know from density is equal to mass over volume, which means the mass is equal to density times volume. So it means the pressure, which would have been mg over area, will simply be equal to the mass, which is density times volume times g over area. But we also know that the volume is going to be the cross-sectional area times the height h. So it means the pressure is going to be density times the cross-sectional area times h times g divided by the area. So we see that this area cancels out. Hence, pressure is equal to density times g times h as required. So as simple as that. Suggest why the equation in A does not give the total pressure on the base of the beaker. So the total pressure on the base of the beaker must be the pressure due to this height plus atmospheric pressure, because there is pressure from the air. So we have atmospheric pressure. So total pressure is going to be pressure due to the atmosphere plus pressure due to the height h, which is density times g times h. So we can simply say there is also atmospheric pressure on the top of the liquid. There is also atmospheric pressure on the top of the liquid. There's also atmospheric pressure on the top of the liquid, so it has not been accounted for. The figure shows the variation of the total pressure inside the liquid with depth x below the surface. Determine the density of the liquid. Okay, so we have already seen that the difference in pressure from the top of the object and the bottom is given by g times density times g times the difference in height from the top and the bottom. So if I want density to be the difference in pressure divided by g times the difference in the height. So the difference in pressure is going to be on the top. So at the bottom it is 9.66 minus at the top, which is 9.60, divided by G is 9.81 times the difference in height is 8 to 0, which is 8 times 10 power, because this is in centimeters, I'll say power negative 2. So I'll press my calculator. 9.66 minus 9.6 divided by 9.81 times 8 exponent minus 2. So this is giving me 0. Let me check the pressure very well. Oh, the pressure is times 10 power 4. So that is 0.00. I'll just multiply this by 1 exponent 4. So that is 764.5. So that is 764.5 kilograms per meters cubed. So I could write 760, or you could write 765. So I'll just write 760 or 764.5 kilograms per meters cubed. Okay. A solid cylinder is held stationary by a wire so that the base of the wire of the cylinder is level with the surface of the liquid as shown in that figure. The cylinder has length 4.0 times 10 power minus 2, cross-sectional area 3.7 times 10 power minus 4. The tension in the wire is 0.53 newtons. The cylinder is now lowered and held stationary. That means it is in equilibrium. So that the top of the cylinder is level with the surface of the liquid. So the cylinder must be having a weight. So the cylinder has a weight downwards, which is W. And they said it is lowered and then held stationary by the wire. So it means it is in equilibrium when the weight, when the upthrust when the upthrust equals to, when the weight equals to the upthrust plus the tension in the wire. So there's another force upwards, which is going to be the upthrust. So for equilibrium, of course, we shall notice that the upthrust upwards plus the tension in the wire should be equal to the weight in that case. So calculate the new tension in the wire. So I'll simply say the tension in the wire is going to be equal to the weight minus the upthrust. So what is the weight? The cylinder has length that and cross-sectional area that. The tension in the wire is 0. Let me see. It is initially a solid cylinder is held stationary by the wire so that the base of the cylinder is level with the surface of the liquid. It is stationary, so it means initially the weight is equal to the tension. The first tension I'll call T1, which is equal to 0.53 because it was initially held stationary and the base was not inside the water. So initially it means the weight was 0.53. Then when it is lowered, the tension T2, the upthrust plus the tension T2 should be equal to the weight. So T2 is going to be the weight minus the upthrust. But we know that upthrust is equal to the cross-sectional area times difference in pressure, which is the cross-sectional area times difference in pressure, which is density times G times the difference in height. So this is going to simply be equal to the cross-sectional area is 3.7 times 10 power minus 4 times the density, which density is I think we calculated the density of the liquid in the previous part. It was 764.5. So the density was 764.5. Then times G, which is 9.81, times the height, because the cylinder is now lowered and then held stationary by the wire so that the top of the cylinder is level with the surface. So the top is now, the whole cylinder is in the liquid, but the top is just level with the surface. So this is going to be times 4.2 times 10 power minus 2. So this is the upthrust. So I'll just press my calculator. 3.7 exponent minus 4 times 764.5 times 9.81 times 4.2 exponent minus 2. So the upthrust is going to be 0.117 or 0.12. So I'll take this as 0.12. Okay, it's because I've used 764.5, so that is 0.12. If I round off, 0.12. Okay. So then that means tension T2 is going to be the weight, which is 0.53, which is the weight, minus the upthrust, which is 0.12. Of course, the weight will not change, it remains constant. When it was in air, the tension was equal to the weight. So we now know the weight. When it is lowered, the weight will not change. So we just subtract that. 0.53 minus 0.12. So this gives us 0.41. So this is 0.41. If you use 760 here, you could be getting 0.42, because here you could get 0.11, depending on how you rounded off there, but this is very correct. So the answer is 0.41 according to my calculation. An electromagnetic wave in a vacuum has a wavelength 8.4 times 10 power minus 6. State the name of the principal region of electromagnetic spectrum of the wave. So for those who don't know the electromagnetic spectrum, Rumenera's mother is visiting Uncle Xavier's garden. Richard's mother is visiting Uncle Xavier's garden. We just estimate from the visible spectrum. We know that on the side of infrared there is red. Red is 7 times 10 power negative 7 in meters. On the side of ultraviolet there is violet, and violet is 4 times 10 power negative 7 in meters. So on which side is 8.4 times 10 power minus 6? This is on the left hand side of red, on the left hand side of the visible spectrum. And if I have 7 times 10 power minus 7, I add power 2. On this I get 10 power minus 5. This will be infrared. That means between 10 power minus 7 and 10 power minus 5, we have infrared. So this region 8.4 times 10 power minus 6 is between 10 power minus 7 and 10 power minus 5. So it must be infrared. So this is infrared. Calculate the frequency in terahertz. So we know that speed is equal to lambda times f. So the frequency is going to be c, which is 3 times 10 power 8, because it was electromagnetic, it is the speed of light, divided by the wavelength, which is 8.4 times 10 power minus 6. And I think this gives us 3 exponent 8 divided by 8.4 exponent minus 6. So that is 3.57 times 10 power 13 hertz. I want it in tera, so for tera I divide by 10 power 12. So it is 3.57 times 10 power 13 divided by 10 power 12 to change it to terahertz. So I'll divide by 1 exponent 12. So it is giving me 35.7 terahertz or 36 terahertz. So this is approximately 35.7 terahertz or 36 terahertz. Remember, when you want to bring a prefix, you divide by its value. If you want to remove a prefix, you multiply by its value. So the answer is 36. An arrangement that uses a double slit to demonstrate the interference of light from a laser is shown in the figure. So this is, of course, we know this as D, the wavelength, and we know for a double slit, lambda is equal to AX divided by D. We know that for a double slit. The light from the laser has a wavelength of that and is incident normally on the slits. The separation of the two slits is A. The slits and the screen are parallel and separated by a distance 2.8. An interference pattern of bright fringes and dark fringes is formed on the screen. The distance on the screen across 8 bright fringes is 22 millimeters as illustrated. So let's see, we have 1, 2, 3, 4, 5, 6, 7, 8. There are 8. So it means the distance between two successive bright fringes is going to be 22 divided by 1, 2, 3, 4, 5, 6, 7, 8. So it is 22 divided by 8. That is going to be x. Distance between two successive bright fringes is 22 divided by 8. Okay, let's see the question. Are the light waves emerging from the two slits are coherent? What is the meaning of coherent? Coherent means constant phase difference between two waves. So that is constant phase difference. Constant phase difference between waves, of course, with time. As time goes on, the phase difference remains constant, that is coherence. Calculate the separation A of the slits. Separation. So we now know that lambda is equal to AX divided by D. So I want A. A will be lambda D divided by X. I'll just substitute. The wavelength was given, I think it is 6.2 times 10 power minus 7. D we have seen it is 2.8 divided by X. Remember, we have seen that X is 22 divided by 8. So I'll say 22, because it was given in millimeters, I will say 22 times 10 power minus 3 divided by 8. That is X. So from my calculator, 6.2 exponent minus 7 times 2.8 divide by, well, just take the 8 up. So I'll say times 8. The 8 goes up, then divide by 22 exponent minus 3. So this is giving me 6.31 times 10 power minus 4. 6.31 times 10 power minus 4. 6.31 times 10 power minus 4. Fringe P is the central bright fringe of the interference pattern in B. Fringe P is the central bright fringe, central. Okay. Fringe Q and R are the nearest dark fringe and nearest bright fringe respectively. So this is the central. P is the central bright fringe where n equals to 0. It means R is the first bright fringe where n equals to 1. So calculate the difference in the distance That is the path difference from each slit to the center. Of course, we know that the path difference, because P is a bright fringe where n equals to 0, and R is the first bright fringe where n equals to 1. We know that for a constructive interference, the path difference is equal to n times lambda. For constructive interference, the path difference is n times lambda. And for destructive interference, because Q is the nearest darker fringe, destructive interference, this is constructive interference. For destructive interference, the path difference is going to be n plus a half into wavelength. So where n can be 0, 1, 2, and so on and so forth. So the nearest darker fringe will be corresponding to n equal to 0 for destructive interference. So since n is going to be equal to 0, it means the path difference is simply going to be a half of lambda for destructive interference. So the path difference is going to be a half wavelength for n equals to 0. So this means the path difference is going to be equal to a half times the wavelength was 6.2 times 10 power minus 7. So I think we divide this by 1 to be 3.1 times 10 power minus 7. That is the path difference. Tell the phase difference between the light waves emitting at the center of fringe arcs. That is constructive. So for constructive interference, we know that the path difference is equal to n lambda and n is equal to 1. So, and n is equal to 1 because n equal to 0 is the one which is at the center. So it means the path difference is going to be the wavelength. So the phase difference is going to be 360 divided by the path difference over wavelength. So since the path difference is equal to wavelength, so this is going to be 360 into wavelength divided by the wavelength. So this gives us 360 degrees. The path difference is equal to 1 wavelength because n is equal to 1. Yet the phase difference is 360 degrees into path difference over wavelength. But since the path difference is the same as the wavelength, so the answer here is going to simply be 360 degrees. Sometimes you can always use the blank pages in order to just be sure of what you are doing. The metal wire in a circuit has length 1.8 and cross-sectional area 1.5. The total number of free electrons, that is capital N, in the wire is 2.3 times 10 power 23. There is a current in the wire so that the charge is 172 coulombs, that is Q, past a fixed point in the wire in a time of 2.5 minutes. Show that the number density of free electrons in the wire is 8.5. So of course number density is small letter n, which is going to be total number of free electrons divided by the volume, because it is number of free electrons per unit volume. So total number of free electrons is given as 2.3 times 10 power 23 divided by the volume. Volume is cross-sectional area times another length. So the volume is going to be cross-sectional area, which is 1.5 times 10 power minus 6 times another length, which is 1.8. So we have 2.3 exponent 23 divided by 2.3 exponent 23 divided by 1.8 times 1.5 exponent minus 6. So this is giving 8.51, 8.52 times 10 power 28, which is approximately the same as that. Then calculate the average drift speed of the free electrons. Average drift speed of the free electrons. So first of all, we know that current is equal to NAQV. NAQV, where Q is now going to be E. Q is going to be E. And current is equal to charge over time t. So the current is going to be charge over time t, which charge is 172 coulombs. The time was given as 2.5 minutes, so I will say 2.5 times 60 to change it to seconds. So making the drift velocity the subject, V is going to be I divided by N A Q, which Q is E. So I'm now substituting. I is 172 divided by 2.5 times 60. Then I will divide by N. N is given as 8.5 times 10 power 28. Cross-sectional area was 1.5 times 10 power minus 6. Yes, minus 6. Then charge of an electron is 1.6 times 10 power minus 19. So let's just press our calculator. 172 divided by 2.5 times 60 divide by, I'll just open several brackets. The first bracket, 8.5 exponent 28 times, open another bracket, 1.5 exponent minus 6 times, open another bracket, 1.6 exponent minus 19. Then close the outer bracket, so that is 43 over that. Then press my calculator. I'm getting 5.62 times 10 power minus 1, 2, 3, 4, 5, power minus 5. So this is 5.62 times 10 power minus 5. Okay. A battery of EMF 9.6 volts and negligible internal resistance is connected in series with two fixed resistors and a thermistor. So this is a thermistor. Let me call this resistance RT to mean thermistor, resistance of the thermistor. The fixed resistors have resistance 3400 and 5400 and 5800. The reading of the voltmeter in the circuit is 6.0. So here the PD here is 6.0 volts. The PD across this and this is 6.0 volts. Okay. Calculate the current in the resistor of resistance 5800. So we now need total current, I total current. Of course, we know that the EMF is equal to the terminal PD plus, I think there is no internal resistance here. So I'll just simply say EMF, the EMF is equal to the current times total resistance, R total. So the EMF is 9.6. Okay, I will not use this. I will sum up the PD. I will just call these ones PDs. PD across this one, PD across here, I will call it V1. PD across here, I will call it V2. But V2 is going to be equal to the current times the resistance there. So this is going to be V1 plus V2. So 9.6 is going to be equal to, this is V1 plus V2. So it's equal to V1, which is 6, total PD downwards, plus the PD there, which is going to be the current I, times the resistance, which is 5800. So I'll just say 9.6 minus 6 divided by 5800. So that it gives me 6.2 times 10 power 1, 2, 3, 4. So I is equal to 6.2 times 10 power minus 4. So this is 6.2 times 10 power minus 4. Calculate the resistance of the thermistor. Resistance of the thermistor. Now that I know the total current, remember they are in series. So I know the total current, and I know that total current, I total is equal to EMF divided by total resistance. Total current is EMF divided by total resistance. So total resistance, it means total resistance is the EMF divided by the total current. So let's find total resistance. Total resistance, they're in series, we add all of them. So 400 plus RT plus 800 is total resistance. So I'll say resistance of the thermistor plus 400 plus 800 is equal to the EMF, which is 9.6 divided by total current, which is 6.2 times 10 power minus 4. So I'll just press my calculator. I'm going to just divide 9.6 divided by 6.2 exponent minus 4. Then I will subtract 400 plus 800. So this is giving me 6.23 or 6.3 times 10 power 3. So R total, R of the thermistor is 6.3 times 10 power 3. So this is 6.3 times 10 power 3. Okay. The initial energy stored in the battery is 2.6 times 10 power 4 joules. Assume that the EMF of the battery is constant. Determine the final energy stored in the battery after a charge of 330 coulombs has moved through it. So if a charge of 330 coulombs has moved through it, what energy is being delivered? So the energy delivered when that charge passes through, the energy delivered is equal to, of course, we know that V is equal to energy per unit charge. So it means the energy delivered is going to be V, Q times V, which is going to be 330 times V, which is 9.6. So this is going to be, this is the energy delivered. So 330 times 9.6. So this is 3168 joules. That is the energy delivered. So what final energy is stored? So final energy stored, the energy which remains, final stored energy is going to be equal to 2.6 times 10 power 14, power 4 minus 3168. So I'll say 2.6 exponent 4 minus 3168. So this is giving me 22832, or I can write 2.3 times 10 power 1, 2, 3, 4 times 10 power 4 joules. The environmental conditions change, causing an increase in the resistance of the thermistor. State whether there is a decrease, increase, no change. There's an increase in the resistance of the thermistor. Resistance of the thermistor increases, but we know that the resistance of the thermistor is inversely proportional to temperature. So if the resistance of the thermistor is increased, it means the temperature has decreased. So this is automatically decreased. Then the current in the thermistor. Remember, the resistance has increased. The resistance of the thermistor has increased. And of course, we know that resistance is inversely proportional to the current. So automatically the current must decrease. So this is a decrease. Then the PD across the thermistor. the PD across the thermistor. So since although the total current has decreased, because it is the same current through all the resistors, we have the fixed resistor, we have the thermistor, we have the other one. So if the total current has decreased, it means the PD across these fixed resistors decreases. The PD across the fixed resistors decrease if the total current decreases. But because energy must be conserved, the PD across the thermistor must increase. So PD here decreases because the current decreases. PD here decreases because the current decreases. But remember, the EMF must remain the sum of the PDs. If this is V1, V2, V3, the EMF is equal to V1 plus V2 plus V3. V1 is across the fixed resistor of 3400, so this one decreases because the current decreases. This one also decreases because the current decreases. So it means by conservation of energy, V2 must increase. Since V2 has a resistance which is increasing, even though the current has decreased, by conservation of energy, V2 must increase. So from V equals to IR, even though I has decreased, since the PD across the rest has decreased, the PD across the thermistor must increase. So this one increases. I have said if this was 9.6 volts, the current through the circuit decreases. It means V1 decreases because V1 is I times R, R1. V3 also decreases, but remember the EMF must remain 9.6, so it means the PD across the thermistor must increase. So that one increases. And lastly, I have only 3 minutes because the paper is 1 hour and 15 minutes. An isolated nucleus X decays by emitting an alpha particle. We know that an alpha particle is alpha 42. It is a helium nucleus. To form a nucleus Y. Nucleus Y and nucleus Z are isotopes. They have the same proton number but different neutron number. By comparing the number of protons in each nucleus, state and explain whether the charge of the nucleus Y is less than, greater than, or the same as. So nucleus Y and Z, these ones Y and Z, because they are isotopes, they have the same proton number, so they have the same charge. These ones have equal proton number. It's the proton number which determines the charge. Equal proton numbers, and so they have the same charge. And so they have the same charge. The nucleus X. An isolated nucleus X decays by emitting an alpha particle. Nucleus Y and nucleus Z, an alpha particle to give nucleus X. So it has lost 2 protons. So it means nucleus Y has 2. If we have X to give us Y plus an alpha particle which is 4, 2. If X is AZ, Y is going to be A and Z minus 2. So it has lost, Y has 2 fewer protons. So Y has 2 fewer protons than X. So Y has less charge. So Y has less charge than X. And lastly, use the principle of conservation of momentum to explain why nucleus Y cannot be stationary. Remember, initially X was stationary, its initial momentum was 0. So if Y and an alpha particle which moves away, if this Y is also stationary, the alpha particle has energy, then it means momentum will not be 0 finally. So it means for momentum to be 0, an alpha particle moves in one direction, the Y moves in another direction with equal but opposite momentum so that the total is 0. So let's say that X is initially initially, x is initially stationary, so total momentum before decay is 0. Total momentum before decay. Total momentum before decay is 0. So total momentum after decay must also be 0. So total momentum after decay must also be 0. And the only way we can make it to be 0, hence y must have equal and opposite momentum to the alpha particle. Hence y must have equal and opposite momentum to the alpha particle. Which means y cannot be stationary. So it means y cannot be stationary because to conserve momentum it should have an equal but opposite momentum to that of the alpha particle. Okay, so I think this marks the end of the first component. See you in the second component. Bye bye.